Welcome to the presentation for the Marine Highway Traffic Monitoring System with trajectory prediction from Automatic Identification System, sensor data using artificial neural networks by Simon Felix A. Briones, GIAN Marco M. CASOPLE, FELINE B. DIMATULAC, advised by Engineer Febus Reidj Cruz. Being an archipelago of approximately 7,107 islands, the Philippine shipping transport industry plays a very vital role in the country's growth and development. This paper aims to tackle the lack of monitoring and as well as the lack of maximizing the potential use of marine traffic through Python programming. The popularity of traveling and deliveries via boats and ferries, however, have not changed the effective, albeit outdated, and improvable monitoring and managing of the sea travels of Philippines, which is the Philippine Nautical Highway System. The Nautical Highway System was effective in connecting isolated parts of the country and reducing transportation costs, but it also limits and hinders the maximization of vast expanse of the Philippine waterways. The system also lacks proper tracking and monitoring of not only cargo and people, but also the nautical routes of each vessel, which is crucial in preventing sea vessel collisions and accidents. The researchers proposed a system that will monitor maritime traffic through AIS data streams and provide trajectory prediction and detect vessels that are out of their suggested route using an artificial neural network. This system installed in a port will provide the operator of the port a second opinion on how the maritime traffic is to be managed. Moving on to the objectives of the paper. So the first objective is to develop a receiver of AIS data using the Raspberry Pi and the RTL2832U dongle with dipole antennas. Okay, so the second objective is to develop a GUI or graphical user interface that will be able to process the received data streams using Python programming or PyQt4 only base.
For our system flowchart, first, we will collect AIS data from different vessels within the range of our receiver. Then, the collected AIS data will be saved to a specific shared directory. The raw AIS data is in AIVDM format. This is an example model of a neural network. It is made up of layers of neurons. These neurons are the core processing units of neural networks. First, we have the input layer, which receives the input. Then the output layer predicts the final output. In between exist the hidden layers, which perform most of the computation. Neurons of the first layer is connected to the hidden layers by channels. These channels have different weights. The input is multiplied to its weight and will be the input for the hidden layer. Then, it will be passed to a threshold function, which is the activation function. It will determine if the neuron will be activated or not. At the output layer, the neuron with the highest value will determine the output. For our study, the use of neural network will help for the forecasting of the trajectory of the vessel. Also, the large amount of AIS data will be useful to ANN since it needs complex of data for the training process. ANN has many types, but for this study, we focus on multi-layer perceptron. And from different experimentation, for the kind of activation function, we come up with hyperbolic tangent. For our neural network structure, it consists of 6 inputs with 1 hidden layer and 40 hidden cells and 6 outputs. For the kind of neural network that we use a multi-layer perceptron. It is a type of artificial neural network that is fully connected. As we can see on our past figure, this is an example of multi-layer perceptron. As you can see, the input is interconnected to all the hidden cells of the hidden layer. Multi-layer perceptron is ideal for trajectory prediction since it has backpropagation for learning. And for the activation function that we use the hyperbolic tangent. Based on the past recent studies, hyperbolic tangent is most accurate to all the different kinds of activation function. We also test the capabilities of the hyperbolic tangent. And as we test the activation function, it shows that for all the kinds of activation function, hyperbolic tangent is the most accurate. This figure shows the actual GUI design.
All the AAS data we've decoded. Some data are corrupted and some data are incomplete, so we've just selected the ones that has the complete AAS data. So we can process it correctly and completely. So the table below shows all the AAS data for a particular ship or vessel. So in this case, for the vessel ID of 538001923, these are its AAS data information. So it has 57 timestamps. So next, on your right is the trajectory prediction of the path shown earlier. So the red one is the trajectory prediction for 5 minutes of this um, vessel. And on your left is the comparison of the trajectory prediction of our program to the actual data or actual path of the vessel from marine traffic. The marine traffic is a website that when you know a vessel ID or the MMSI of a particular ship, you can search its path and you can also export it from that website. So we've exported the data and plotted it in the Google Earth Pro and plotted our um, predicted values also in the Google Earth Pro and shown it there for illustration. This table shows the exported data from marine traffic of the vessel that has an MMSI of 538001923 from the last slide. So its vessel name is Resolute, its event in terrestrial range. That's why we can receive its AAS data. The date and time is from 5:01 p.m. to 6 p.m. Its area is Philippines, and here is the latitude and longitude. So this is the table for the predicted value from the program. So it started with timestamp of 57 because it is the last timestamp of the received AAS data of our receiver. And the last timestamp is 77 because the program predicts for 20 timestamps. We used RMSE or root mean square error for the analysis of the error of the predicted value with respect to the exact value, actual value from the marine traffic. So with this table here, from the equation earlier shown in the statistical analysis, we can now get the RMSE for the latitude, which is 0.006, and the RMSE for the longitude, which is 0.015. Then we input these two values to the Haversine formula as discussed earlier in this statistical analysis. So we get this value x, which is 1.79 kilometers. So when we compare it to the baseline or the reference that we discussed earlier, which is the safe distance between two vessels, which is 1.22 for nautical miles or 2.267 kilometers. This value here is much lower than 2.267 kilometers. That's why we can safely assume that this prediction is accurate or viable with respect to the actual value. The uncontrolled testing to tell whether the ship is out of its route or not, we, we used the data from marine traffic to verify our program. So first, we chose a specific vessel ID. Then, we search it in our program. So the blue one is its path. Then, we search it in the marine traffic to tell where it has come from and where it is going. So, for this example, from Tagbilaran to Manila. So, we made sure that we plotted or we manually plotted that specific highway. So we plotted it with the black lines here. Then we predicted the chosen vessel. Then from that prediction, you will know in this bar below that the route is Manila to Tagbilaran. The ship is in its correct suggested route. So it verifies the route of this specific vessel ID 548654200. So that's that for the uncontrolled testing.
Trajectory prediction, being that the course over ground is the actual direction of the progress of a vessel between 2 points with respect to the surface of the Earth.
So the data gathered throughout the entire span of the research includes the overall accuracy and efficiency of not only the program but also of the paper itself. So through rigorous testing, it was determined that the range of the receiver is 24.5 kilometers. This was determined by gathering as much AIS data as time allowed and observing the farthest reach of the receiver. So the farthest reach of the receiver is indeed 24.5 kilometers. Um, the data trajectory prediction results also exhibits accurate results, which were confirmed through various other AIS tracking programs and sites, which do not predict trajectory but rather track and the actual real-time course of the vessel that were observed. So it was also observed that the machine learning capabilities of the program showed to be quite impressive. It showed significant improvement and as more and more data was fed to it. So since as more and more data were fed to it, the more the the capabilities of the program improved. Therefore, the machine learning capabilities of the program is functional and very much reliable. Okay, so for the recommendations. The first recommendation is that it is recommended that the software be installed in a laptop with a fast and responsive graphical processing unit or a GPU for optimal and speedy results to aid in the training of the data that is used in the artificial neural network. So, common sense, the faster the laptop, the faster the program, and the easier it is to process the data. It is also recommended to use a high capacity memory card to accommodate more data. So the higher capacity the memory card, the more data that can be processed and stored as well. When using AIS receiver, it is better to set up at a higher altitude area or somewhere closer to a port to receive more AIS data, since the more closer we are to a port or the higher the altitude, the more vessels are within the reach of the 24.5-kilometer range of our receiver, and the more AIS data that we can receive. It is also recommended to alter the program to enable the plotting of multiple vessels at a time instead of just one at a time. So as you can see from our GUI and as you can see from our program and as well as the paper stated clearly, we can only see the predicted trajectory of one vessel at a time. So it's better to um, alter the program to enable multiple vessels at a time for better results.